light fountain, okay? This is the picture just to show the water fountain, okay? And this is our measurement. You see, this black one is the photonic crystal without nanowire. You can see the segment is very, very small. However, after the deposition of the semiconductor nanowire, the emission with intensity can be enhanced by more than 1,000 times. Okay, so it's a huge difference. Okay, that's a very interesting phenomenon. That's a share cathode luminescence, not the PL. Okay. Okay, you can see this is not noise. Okay, this is this very sharp packet is we call it a random laser. Okay, I'm not going about talking about the random definition of random laser. That will take me too much time. Okay, just compare this spectrum and also this spectrum. You see, this is the photonic crystal without nanowire. You can see just this is almost noise without no sharp packet. So that kind of sharp packet is a stimulate emission pack. Okay, we have a threshold here. Okay, so right now here in this part, I told you the integration of the photonic crystal and the nanowire. We can have a very new phenomenon called the light fountain. This light fountain can have a very strong emission, and also through this system, that is very easy to see the behavior of stimulated emission. Okay, stimulated emission is proposed by Einstein. All right. Okay. Okay, the first part right now I will talk about the integration of the liquid crystal device with the semiconductor nanostructure. Okay, the principle or the working principle to understand the liquid crystal is that the liquid crystal is the liquid crystal is like the molecule of a liquid crystal is like this. Okay, that's a long chain. Okay, and in the liquid crystal device, the long chain molecule is have a will align along a certain direction. After you apply external electric field, you are able to drive the orientation of liquid crystal molecule. Okay. And then therefore you can control the light path of the you are able to control the instant light, the property of instant light. Okay, and then here we integrate semiconductor nano tube or nano wire with the liquid crystal device. You can see our thinking is as follows. If we add semiconductor nanowire into the liquid crystal device, because the liquid crystal molecule is along this direction. After we add the semiconductor nanowire into the liquid crystal device, because the liquid crystal device right now will also have a preferred orientation along the same direction as the liquid crystal molecule, because that is the lowest energy. Okay, if we apply electric field to drive the orientation of liquid crystal molecule, we are able to because due to the strong interaction between the semiconductor nanowire and the liquid crystal molecule. So if we apply electric field to change the direction of liquid crystal molecule, it will also simultaneously change the direction of the semiconductor nanowire. So here you can see, okay, we provide a very good, simple way to make a well-aligned semiconductor nanowire. This is the first one. The second one, we have the opportunity to use the electric field to change the direction of a semiconductor nanowire. And just remember that, okay, because the geometric structure of a semiconductor nanowire is very anisotropic. Okay, so therefore its physical properties strongly depend on the direction. For example, electron can easily pass through along the axis, but it's very difficult to move around the perpendicular, the direction perpendicular to the long axis. Okay, so the physical behavior along the axis and perpendicular to axis is very different. So if we saw in this way, we have a good possibility to use the electric field to change the orientation of semiconductor. Also which means we can manipulate, use the electric field to switch or to control the semiconductor device. That's our principle. Okay. So this is the figure to show you what I say. Okay, we say the semiconductor nanowire here into liquid crystal device. The red one represents the semiconductor nanowire, and this the black one represents the liquid crystal molecule. Okay. Due to the strong coupling between these two, and the semiconductor nanowire or nanotube will align along the direction of liquid crystal molecule. Okay. After applying electric field, we are able to change the orientation of liquid crystal molecule and also the direction of semiconductor nanowire or the nanotube. Okay. So you can see this is after we add the semiconductor nanowire into the liquid crystal device, the optical property is very strongly anisotropic, which gives us evidence to show that the semiconductor nanowire right now is well aligned. Okay. So if we apply electric field high enough right now, so right now the semiconductor nanowire is along this direction. If we measure the detector press here, if we rotate the polarizer, we are able to detect the anisotropic effect of the device. However, after we apply voltage, right now semiconductor will switch to this orientation. So if we detect a press here, even though we rotate the polarizer, we are not able to see, to measure the any change, because right now it's circular symmetry. Okay. So this is to tell you what we have. Okay. This figure to show you what I just said before. Okay. And then we can change the voltage to change the orientation of semiconductor nanowire. Therefore, degree of polarization can also be changed. So this is to show you the degree of polarization consistent with the theoretical calculation. Okay. If this evidence is not enough, we can replace this right now. Replace the liquid crystal by DI water. DI water is a randomly oriented molecule. So if we place the semiconductor nanowire inside DI water, the nanowire that will be randomly oriented. Therefore, we cannot see the anisotropic effect. This is shown here. Perpendicular and the parallel polarization doesn't have have very similar emitting spectrum.
What's the size of nanowire or nanotube?
What's the size? The size long chain around 100 nanometer, and the diameter around a couple nanometer. Okay. Okay, and also if we replace the semiconductor nanowire by nanoparticle, you know, nanoparticle is a spherical symmetry. Therefore, we cannot see the anisotropy effect. So this is the additional evidence to provide what I say. Okay. So here we integrate. We have a new device, semiconductor device system that integrates liquid crystal device and the semiconductor nanowire to provide a device. The device have a very unique feature, which proves that the physical property of this device can be tuned by electric field. Okay. And the fifth part is also about the liquid crystal integration of liquid crystal and the semiconductor. And this is our thinking is very simple. Said to control the liquid crystal device, we have to apply an electric field or an external voltage. So right now we ask a question, say, can we switch, operate, or manipulate a liquid crystal device not by external voltage, just by a light beam? Can we do that? And we say, yes, we can do it, but based on what kind of principle we can resolve this issue. The problem is very simple. So inside the crystal device, we integrate with the semiconductor, say, solar cell. You know the solar cell, right? Solar cell, the principle of solar cell, if you have instant light beam, you can produce a photovoltaic. Okay, this is called this is the solar cell. So if we right now we integrate the liquid crystal device and inside the liquid crystal, if we can build up a stunning device which can absorb light beam and produce photovoltaic. Using this photovoltaic, we are able to switch the orientation of liquid crystal molecule. Therefore, right now we don't need to have an external applied voltage to tune, to change, or to operate the liquid crystal device. Right now, we just by instant light beam, we are able to let the liquid crystal device works. Okay. So this is a simple idea, right? Okay. So we just go ahead to do it to fabricate a device. That device has the liquid crystal, and inside the liquid crystal device, we have a built-in solar cell. Okay. And this device is like this, okay? This is just different from the conventional liquid crystal device. We have a built-in solar cell. This solar cell is very simple because this is just a proof of concept experiment. So we use a very simple solar cell. That's the semiconductor and the metal. Okay, that's a Schottky barrier. Schottky diode can also also alternative way to produce the photovoltaic. Which means in order to produce a photovoltaic, we don't. It's not necessary to have a p-n junction. Okay. You only need to have an internal electric field to produce the photovoltaic. Okay, this is what we have done here. Okay, and then the following, just to show you that with the instant laser light beam, we are able to change the behavior of liquid crystal devices. So this tells us that we are able to use a light beam to control a liquid crystal device device, which is very different from the what we what we think in our daily life. Okay, in our daily life, when we use the electric crystal device, we need to have a applied voltage. But here we don't need to have that. We only need to have a external light beam. Okay. Okay, this is just I talk about this will show you the instant power, laser power is different. We can produce a different voltage. Therefore, the orientation of the liquid crystal molecule is different. It can be so the tilting angle, which means we can calculate from the spectrum. We are able to estimate the tilting angle of the liquid crystal molecule. And this liquid crystal molecule, the tilting angle of the liquid crystal molecule is strongly dependent on the laser power, which means give us another evidence to show that the change of the liquid crystal molecule is due to the instant laser power. Okay. So the main idea in this part is just to show you that we have a new device which can control the liquid crystal device without external applied voltage. Okay. Okay, the final one I will talk about is the integration of the graphene and the semiconductor to produce a new light emitting device. Like this new light emitting device is very different from the conventional one. The conventional one is based on a light emitting device based on a PN junction. Okay, but here we don't need to have a PN junction. We just need to have a semiconductor thin film and a very tiny, very thin insulating layer, and on top of that we have a graphene sheet. Okay, and this is very simple structure. Use this simple structure, we are able to have a light emitting device. Okay, of course, because that is not based on the PN junction, therefore the working principle is very different from the conventional one. And this is to show you that our device is very simple. Okay. This is to show you the property of the graphene, and this one is to show you the transmittance of the graphene compared with the gold thin film, and the transparency of the graphene is very high. We use graphene here is because graphene have two very unique properties. We use here. The one is highly transparent. The other one is the graphene provides good graphene is a good conductor. So we use these two unique properties of graphene to produce this light emitting device. Okay. And then through this IV characteristics, we are able to estimate the mobility of the graphene sheet, and the mobility more than 1,000. That is pretty good, comparable, which is comparable with the indium tin oxide. Okay. And then this one is to show you the semiconductor thin film have the optical emission property of the semiconductor thin film. Okay, so after the device, you can see we apply external bias, we are able to have the emission spectrum. So which means apply external field, we are able to get the light output. This is called the light emitting device. Okay, that's very simple. Okay, and the problem is you can ask what's the underlying mechanism to explain this kind of behavior. Okay, this underhole bias this is under reverse bias. So under forward bias, under reverse bias, we have a different kind of spectrum, which means we can have if we the body is positive, we can have the emitted light with different wavelengths than that of the negative bias. So for this device, we have a different color, okay, depending on the bias positive or negative, which is also very different from the conventional LED device. For the conventional LED device, you can only apply the under forward bias. You can obtain the light intensity. Or for the reverse bias, you will get nothing. Okay, so that's also very different.
So this tunneling?
That's tunneling. That's true. That's called. This is show you this tunneling because this is insulating layer here. Okay, after apply, for example, apply reverse bias, we can accumulate electron near the surface, so the hole pass through. Tunnel through this insulating layer and then recombine with hole. Okay, so this is a working principle. You see, it's very simple. Okay, you just apply external bias and then you accumulate the charge carrier near the surface. We combine those carrier charge carrier recombine with the charge carrier tunnel through the insulating layer. So this insulating layer serves two functions. The one is to prevent leakage current. The other one is to help to assist accumulation of the charge carrier near the surface. Therefore, we have a strong recombination through this kind of device. Okay. This is to show you follow the tunneling mechanism. Okay. So for the last one, continue with this work because this device, light emitting device, is very simple. Okay. Following this research, we have an extended one. On top of this light emitting device, we deposited a very simple also memory device, and combined together, we produce a new device with dual function, right, called a light emitting memory. Okay. I think we should file a patent for this one because I think this is a very simple and cute device. They have a very unique function. Okay, this is the light emitting memory, and that's very different from the conventional memory device. For the conventional memory device, you can just use apply voltage and you so you can code your data in your device. If you want to read your device, you also apply voltage to read current. Okay, but for this device, light emitting memory, we are able to read the signal not only by current, also by light. Okay, we are able to detect the signal by electric signal, electric current, also by optical intensity. So this is very unique. And if a memory device can be read by both electrically or optically, that's very unique. If we can read the signal by optically, the speed can be greatly enhanced. Okay, so
the size could be much larger than conventional.
No, that's not necessary. that's not necessary. Okay, so our device is very simple. Okay, this is the device I talked about. I talked to you. Semiconductor thin film, a very tiny, very thin semiconductor insulating layer, graphene here. And then on top of that, there's an insulating layer and a metal contact. So device also very simple. the bottom one I talked to you, this can serve as a light emitting diode. The top one is serve as the memory device. Okay. Then let me talk about why the top one can serve as a memory device. This is called a resistive switch memory device, and this kind of the research is also a very hard topic right now because the structure is very simple. You just have a electrode, bottom electrode, top electrode. In between, you have an insulating layer. Okay, so this memory device is very simple. They are very advantages showing here. Okay, simple structure, very side fabrication, low operation voltage, low cost, low printing. Okay, scale down and 3D stackability. Okay, high speed for writing, erasing, and reading. Okay, so this is a very hard topic right now because of the simple structure. Okay. Okay, this is to show you that this simple structure, if you apply a voltage under exceeding a certain magnitude, the current have a change drastically. Okay, in here we change the current change is it's around 10,000 times. Okay, so this can become a memory device, and it's a good memory device. Okay, so just like this simple structure, here is a graphene, and here is the silicon dioxide. On top of that is the Ag metal. Okay, and this device is also very stable. Okay, switching cycle after 100 times still remains the same function. Okay, and then we put these two together. One is a light emitting diode, the other one is the memory device. Put it together. Okay, we can read the signal, or we can measure the current has a large difference. We can also measure the light intensity. Okay. Okay, that after a certain voltage, we can have a strong jump of the light output. So in this device, we have two functions. One is we can read the signal electrically, also read the signal optically. Okay, so this is showing here. And this the light emitting memory is also stable after 100 cycle, and the function still remains the same. Okay. Okay, here, so this is a very simple structure where light emitting memory, and it's very easy to fabricate. And the unique feature for this device, memory device, is we can read the signal electrically and also optically. Okay, I will stop my talk here. Okay, thank you for your attention.
Wow, that's really many things in the talk. Okay, is there any questions? Okay, we have many different things like photo detector, solar cell, LED and everything, and Professor Chen has explained it to you in a very, very simple manner, simple way, the simplest way you can imagine.
Okay, let me ask you a question. Any student here who want to ask the question, say why a quantum dot have a high absorption coefficient? Okay, who want to answer the question? This is has been written in the holiday. Okay. So supposedly that if you study well, or you are the fundamental physics, you should be able to answer this question. Yeah. It's very quiet. 这个不列入记录，我这样可以解释，我这样解释，所以我用中文讲，就不要传到国外去，我这样解释，就是 my own way，OK。